Hello, everybody. Welcome back. Today we have the second of the three lecture series by Giulia on quantum gravity phenomenology. Yesterday we learned about some rudimentary aspects of quantum gravity phenomenology, right? And then some model building. And then Giulia went into some details on spectral dimension and other things. So today she will continue, and we will have the third lecture next week. So don't miss it, right? So you don't get to hear about quantum gravity phenomenology every day. So thank you for participating. Giulia, thank you.
Thank you for the introduction and thank you for the advertisement. So before I go on, is there any question from yesterday's lecture? Anything that people would like to clarify? Okay, if there is... is anyone talking?
No, I think we're good.
Okay.
Oh, somebody has. Saulo, you can ask the question.
He's in the chat, right?
Just a moment. I'm reading. Okay, let me say here. Yesterday, you told us about a kind of Brownian motion on light signals traveling in the cosmos, okay, in the universe. Is this applied to a particle as well? Could you expect a Brownian motion of a particle because of the quantum fluctuation of space-time?
Okay, this is a very interesting question. So I mentioned the Brownian motion as an analogy in that case. So it was just to say that you can look at things far away from the scale of the structure that you want to study and still get information about the structure. But then when I was discussing, and this will happen even more today when I was discussing what may happen, for example, in a non-commutative spacetime. You remember I mentioned the possibility of having a modified dispersion relation. And in that case, also because I was in that semi-classical approximation where I was sending h bar to 0, so particles were classical objects, and also the treatment of space-time was classical at that point, even though it had some deformation. So in that case, you get the modification is in the same direction. There is a correction term that is the same for any particle. However, if you want to include possible quantum uncertainties in the space-time, then, for example, you may get that instead of having this systematic deformation, let me call it this way, then you may have a fuzzy deformation, meaning that there is some central value, and what you may get from an individual particle has some probability distribution around this central value. Okay, so in that case, you would have not a systematic effect, but a fuzzy effect. And I will say a few words about this later during the lecture today. In case I don't, please call me out and ask that I say something. Okay, because I didn't write it in the slides. I meant to. In fact, I forgot, but you're reminding me. So in case I don't say anything about fuzziness, please remind me, okay?
Okay, Giulia, thank you.
Sure. Any other question? Okay, then maybe we can start with today's lecture. Okay, so the plan for today is possible implications for running dimensions in cosmology. So we talked about running dimensions yesterday, and I'm going to show possible implications. Then also possible implications of the modified kinematics that we discussed yesterday for astrophysics. Then I will discuss different possibilities concerning what happens to relativistic symmetries when we are studying quantum gravity models, and how these are distinguishable at the phenomenological level. Yesterday, I promised that I would talk about also a test case scenario today. In fact, I realized that I will not have the time. I hope I can manage to cover the first three topics. So this last thing will go in the lecture of next week. Okay. Okay, let me just start with a one slide recap about what we learned yesterday about dimensional running. So we learned that we have indications within different quantum gravity theories that the spectral dimension runs from the value of 4, say, in the infrared to a different value in the ultraviolet, meaning at very short length scales. We gave the definition of the spectral dimension. Here, I don't want to repeat it. What we should keep in mind for what comes next is that this running of the spectral dimension that, as we said, has been found independently in several theoretical approaches to quantum gravity, can be understood in terms of an effective deformed Laplacian of the theory, meaning an effective modified dispersion relation in Fourier space, and or, so the two things can happen at the same time or not, as a modified effective metric in the Fourier space or in the momentum space. In fact, when you're looking at the return probability, which is the object from which you derive the spectral dimension, you write it in Fourier space, and you can modify either the metric that you're using or the dispersion relation that enters here. I want to briefly show you this example that I flashed in the slide yesterday, but didn't have time to discuss. Let us assume that we are in a momentum space that has flat geometry, so standard scenario. However, let us assume that the effective Laplacian of the theory is modified, and in particular, it can be encoded in a deformed dispersion relation of this kind. So you see that here we have a correction term. 1 over lambda would be the energy scale where the effect becomes relevant. So it would be the ultraviolet scale, maybe associated to the quantum gravity scale. And then we have a free parameter gamma that tells us which power of lambda p we have here. Then you can compute the spectral dimension, and you get that in the ultraviolet. So when you see that it runs, this is for gamma equal 1, this is for gamma equal 2, and here we are at large values of the diffusion time, and here we are at small values of the diffusion time, meaning we are in the ultraviolet regime. And you see that if we go to the ultraviolet regime, the two models, well, very basic models, but the two models run to different values. For gamma equal 1, we get a running to 2.5 dimensions, and for gamma equal 2, we get a running to 2 dimensions. And in general, we can write the spectral dimension in the UV as a function of the spatial dimensions in the infrared and this parameter gamma. Okay, now let's go to cosmology. So you know that in our current model of the universe that is expanding, and if we go back in time, the primordial fluctuations that eventually seed all the structure of the universe that we see today, including how galaxies are distributed and also what is the pattern in the cosmic microwave background. These primordial fluctuations, if you go sufficiently back in time, at some point we'll have a Planckian wavelength. Okay, this is just because they shrink, and eventually you get there. And for this reason, they are a very sensitive probe to any modification of the structure of space-time at the Planck scale, because it is as if you're probing your space-time with a probe of Planckian wavelength, okay? Starting from the for observations of the cosmic microwave background, what people usually do is they extract a power spectrum of the perturbations that you see here. Here, red is higher temperature, blue is lower temperature. There are correlations at different distance in the sky of these perturbations, and they have a power spectrum that is measured. When you compute the power spectrum, usually you go to Fourier space because that's easier, and you will get that the final power spectrum includes the power spectrum of the primordial perturbations, which is this P, and then it is mediated by a transfer function, this delta squared, and this transfer function knows about everything else, meaning the geometry of the universe on the large scale, all the history of the universe from just after inflation until today. Okay, it tells us how the primordial power spectrum of the perturbations evolves and is projected in the sky to produce the pattern that we see in the cosmic microwave background. Okay, so I mean, you can get information about the primordial power spectrum observing the CMB. However, it is mediated by this. Okay, so it's not that you can really see it directly. Still know a few things about this primordial power spectrum based on what we observed today. And for example, we know that it is approximately a scale invariant power spectrum, meaning that it doesn't really depend on the wavelength of the mode that you are considering. So this depends on K, and we know that it doesn't really depend on K. It has a very slight dependence. So we say that it has a red tilt. So how do you compute this primordial power spectrum in the standard scenario? This is just one slide summarizing a full cosmology course. So I don't expect that people who are not really familiar with it will get everything, but at least it will give you the general idea. So you start from your Einstein-Hilbert action in Friedman-Robertson-Walker background. You perturb it because you are interested in these perturbations, and then you see what is the equation of motion for these perturbations. And you get a second order equation of motion. V is the variable defining the perturbation. Z is basically the scale factor. And you see that here we have a second order equation, and it contains two terms. One is a pressure term, and one is the evolution given by gravity. So there are these two terms. And when we are looking at the very small length scales, so when K is much larger than A double prime over A, this is basically Z double prime over Z, then you can find an approximate solution. And this is for the perturbations that are still within the Hubble horizon. Okay, at some point these perturbations exit the Hubble horizon and they propagate and evolve, and we can eventually see them. When you're at large length scales, so for the perturbations that already exited the horizon, you can find another approximate solution in terms of an ansatz, basically. This is some function that you want to fix. And then your power spectrum will be given by this solution, basically. You do not compute it in terms of the V variable because you want the curvature fluctuation that is physical. So you go into the comoving gauge. This is the relation between the one that you use, Z, and the one that you start computing your evolution from. But okay, these are say details. In any case, you know that the power spectrum is going to be given by, this is a normalization factor for the power spectrum times your fluctuation squared, okay? And we are interested in the late value of V because this is after we went out of the Hubble horizon. So to find what is this function F, basically we ask that at the moment you have the transition between the two regimes, these two functions match, okay? The moment you have, when is it that you have the transition is when these two terms are equal. And you know that A double prime over A, if you are in a de Sitter expansion phase, which is what you have in basic inflation scenario, it's eta to minus 2. Eta is our time. So you can find F, you put it inside the form, the function, the formula of your power spectrum, and you will see that what you get is something that is invariant with respect to k, because here you have a k cubed, and here you have a k to the 3/2 squared. So it's a constant with respect to k. And this is basically said in a very few words how you get a scale invariant primordial power spectrum in a very basic de Sitter inflationary scenario. Okay. The way I presented it, all the story here is the way that is best fit to study what happens if we want to account for a possible dimensional running. And a possible way to do it is that we can assume that while the background, so the background evolution of the universe is a standard one, the fluctuations are affected by some quantum gravity effects, because the fluctuations are the ones that are Planck scale, okay? So they are going to be more sensitive to that. And we can assume that the dispersion relation in Fourier space of these fluctuations, is modified. And we can take as toy model the modification that we have seen leads to the running of the spectral dimension. We have seen it in 2 slides ago. So basically, when you consider this, you will have that the speed function, the one that appears here, will get a k dependence, and therefore a time dependence, because k is, p is dependent on time. P is k over a. One is the co-moving momentum, the other one is the physical one. So what you're getting here is that instead of having your c that was a constant earlier, it was just, now you have that it becomes a function of k and time, and it depends on your parameter gamma that is in the dispersion relation that you're using to model the running of spectral dimension. So now you get a modified evolution equation for your primordial perturbations. And you can still play the same game that I discussed before. So you can look at the solution for small scales. It will depend on gamma. And the solution at large scales, where it will not depend on gamma. Because it is at small scales that the deformation is relevant, right? Because it's a deformation that is relevant in the UV, so for very small scales. So it is here that the deformation appears. And then, as we did before, we want to match the two solutions at horizon crossing and put the solution inside the definition of our power spectrum, okay? Once we do it, we get something that in general will depend on gamma, and in general will depend on k, so you will not have scale invariance. However, in the case when gamma is equal to 2, which, as you may remember, was the case where in this toy model we had running of the spectral dimension to 2 dimensions in the ultraviolet, then the k factors cancel out. And what also the A factor, so the expansion factor, cancel out. And what you're left with is something that is indeed scale invariant. And this is already very interesting because it is showing that a possible reason why the power spectrum is scale invariant is not, in fact, that we have a de Sitter phase in the universe, but it may be that it is just because you have a standard FRW expansion, so not the de Sitter expansion, but FRW expansion. But your theory is behaving effectively as if the dimension was running to 2. Okay. Indeed, if you really want to keep inflation, so you really want to keep the Sitter expansion, you don't really need it. You don't really need these to explain the scale invariance. You can still put it in. It will not really disrupt too much what you find. However, it is very interesting that this is happening. Now here, before we go on, I use this very basic toy model of a specific deformed dispersion relation, which I put in the equation for the evolution of primordial perturbations. We don't really know if I were to use some more complicated model, say a model with the curvature in the momentum space and the different dispersion relation, still such that the running would be to 2 spectral dimension, but with a different structure in the momentum space, in the Fourier space. We don't really know if this would still work. What we know is that this can be shown that at least in flat spacetime, any model that has this running to 2 dimension then will produce a scale invariant spectrum. Okay. However, the generalization of this to curved spacetime is very complicated and has not been done yet. However, it is interesting. Also here, I'm not really arguing that this is the reason why we see the power spectrum as it is. My main motivation here is to show you how features of Planck scale physics that have good theoretical grounds can be used within different physical frameworks and to see what happens, okay? So we were saying that, okay, for gamma equal 2, we get a scale invariant spectrum. However, here we see another thing that is quite interesting, which is that the amplitude of the spectrum is given by the ratio of the Planck length and this scale lambda, which was the scale where the UV correction to the dispersion relation was dominant, okay? If you remember, lambda is the parameter that was appearing here. This means that since we can measure this amplitude, we can infer it from what we see in the CMB, then we can use the amplitude of the power spectrum to constrain lambda. And in fact, we know that this amplitude is 10 to the minus 10. And from here, we get that this value of lambda would need to be 10 to the 5 times the Planck length in order to match what we observe. Another thing is that, in fact, as I mentioned, we don't really observe exact scale invariance. We observe a slight tilt, which usually is parameterized as P of k going as k to an s minus 1 with an s less than 1. And you may wonder, can I reproduce this in such a model? Yes, it is possible. It will be, what you get is a constraint relating gamma, so the power of the correction, to W, which is the equation of state parameter of the fluid, of whatever you have that is determining the background evolution of your universe, so how fast it is expanding. The equation of state parameter has constraints, and putting everything together, you get that to get what we see about an S, you will need to have that this gamma is in fact somewhere between 1.98 and 2. Or you may imagine that when the perturbations are produced, they are still not fully in the regime where the gamma equal 2 term is dominant. They are close to that. And so you're not really seeing gamma equal 2, but something smaller. And there is something more that you can say. So you can ask yourself what happens to primordial gravity waves. So the power spectrum I was discussing before is the one of scalar perturbations. However, we expect... You have a question?
Excuse me, Julia. I think there's a question in the chat related
Sure.
to before we pass on.
Sure. Let me see the chat. What is it? Oh, here it is. How certain are we that the density perturbations in the early universe was on Planckian scales? Does this rely on the assumption that our current models are valid down to these scales? Well, what we know is that they become smaller and smaller. Given the scales that we see today, we can evolve them back in time and see when they would become Planckian, right? So eventually they will become Planckian unless maybe some quantum gravity changes radically the evolution of the universe at very early scales, at very early times, okay? So it's not that we are certain. This is, again, a matter of inferences. If we assume that the evolution is what we know today, then eventually these perturbations will become Planckian. This question is very good because, as I mentioned yesterday already, we always have to be aware of the assumptions that we are making when we are comparing models to what we see. So it is a very good question. As I was mentioning, the assumption here is that the background evolution is still governed by the standard Einstein-Hilbert action. And the only thing that is affected by the modification is the perturbations, because it's those perturbations that have a Planckian size, okay? However, you may ask, okay, what if the Einstein-Hilbert equation doesn't work any longer before the perturbations become Planckian size? It may be, we don't know, okay? It is something to be investigated, in fact. What we know is that within the standard inflationary scenario, eventually they are Planckian, going sufficiently back. I think you're muted. I'm not hearing.
Yes. Thank you. Could you please go back a couple of slides where you showed the CL? And we have two functions, right? One is the power spectrum, the other is the delta. There you go. Yes, in the multiple functions. So the delta L, what kind of physics does it depend on? You showed us how to get the power spectrum, the P, right? Yes, exactly.
Well, this depends on late time physics, about
not the early one.
Effects of, I don't know, dark energy, dark matter. I mean, it's on large scales. We know that our model works, our cosmological model works, because we get quite a good agreement with the CL that we see. This delta, of course, for example, would change if you consider infrared modifications of gravity, right? So it depends on your infrared gravity model. And in fact, this is one of the ways you constrain your infrared gravity model, by asking that the CL, so the CMB power spectrum you get with your computations, is actually what you see, okay? But in principle, I mean, unless there is some quantum gravity effect that influences the infrared, which is a possibility, even though it is not one that is much studied, but it is a possibility. In principle, it shouldn't depend on quantum gravity effects, if quantum gravity only affects the ultraviolet, so the very small length scales.
Got it. So delta depends on the late time physics and P depends on the early physics then.
Exactly. Okay. Yes.
Okay.
So here in all of these, I am assuming that this delta is the one that we know. I mean, the one that we use. Okay, I'm assuming that it is not modified.
Yeah. Thank you.
Sure. Okay, if there are no other questions, I can see. I see there is.
We're good for now. Yes, we're good for now.
Okay, then I can move on. Where oops, I think we were here. Yes, I wanted to very briefly discuss also what happens with primordial gravity waves, meaning perturbation in the tensor mode of the gravitational field. Well, we haven't seen any yet, so here it's not that we have much observational indications. We only know that the ratio of the amplitude of the tensor perturbations over the amplitude of the scalar perturbations has to be less than something, okay? And this something is becoming smaller and smaller. However, we may ask, assuming that eventually we may see it, okay, what happens if we assume that also for the tensor perturbation, we have that they are affected by this modified dispersion relation that is encoding some dimensional running. In principle, we may even have that the power that we have here is different with respect to the scalar modes, because maybe scalar modes and tensor modes see different effective dimensions. We also may have that the scale at which this modification becomes important is different with respect to the scalar modes. So we keep them as 3 parameters. You can repeat an analysis similar to the one that I discussed and compute this ratio, which is the thing that we can constrain today. And you will find that, of course, it depends on gamma, which is the parameter for scalar, and gamma t, which is the parameter for tensor, and then lambda and lambda t. In this way. Now, assuming that, but this is an assumption, we don't know anything about it, but assuming that also the primordial spectrum of tensor mode is scale invariant, meaning that basically gamma is equal to gamma t in this model, so, and they are both equal to roughly 2, then you will get that this ratio is basically the ratio between the scale of the scalar modes and the scale of the tensor modes. And this allows you to put a constraint on the scale where this effect for tensor modes becomes relevant. So starting from, say, R minus then 0.07, which is one of the recent constraints, then you would get that lambda t has to be larger than 4 times lambda. So the scale at which the tensor modes see strongly this running of dimension is at least 4 times larger than the scale at which this is seen by the scalar modes. Okay. There are many more things and subtleties that you can do here, but I don't think they belong to this course, so I'm skipping them. Here I put some references to some work where you can find more details. I mean, as I said, the main message, before going on with the next topic, the main message that I want you to get from here is not that this specific toy model that I am using is good. The main message that I want to convey here is that you start from some general feature that you see in quantum gravity theories, many of them, so you think it is interesting. You find a way to describe it that is good for phenomenology. In this case, it was the observation that instead of considering the full model for what concerns the spectral dimension, you can use an effective deformed dispersion relation. And then from there, you can see if this was true, what would happen. And in this case, we were looking at the early universe because this running of the spectral dimension is a really ultraviolet effect. So it is something that you see when you are sending this diffusion parameter to 0, meaning when you are going deep in the quantum gravity regime, okay? So for this, you needed to go somewhere where this deep Planckian regime is available, and this is the early universe. And And indeed, you can see that it has implications there. Also, I want to emphasize that when doing all this game, when playing this game, you have to keep in mind what assumptions you are making. For example, here, one of the main assumptions is that, in fact, the background is evolving according to standard Einstein equations, okay? So if there are no questions, no more questions on this part, I would probably move on to the second part. Let me see the chat.
Oh, we are good for now, Giulia.
Okay, so let's move on. Very brief recap now in 2 slides about what we said yesterday about deformed kinematics coming from non-commutative spacetime models. As I also mentioned earlier today, we are considering this regime, so it's a semi-classical regime where you have an energy scale, no length scale. In this case, from your non-commutative spacetime, you get deformed phase space. This deformed phase space is compatible with the deformation of the symmetry generators that you usually have in special relativity, time translation, space translation, and boost. And within this framework, we know how to compute the infinitesimal action of these generators on phase space coordinates. Another thing that we have discussed yesterday was that from there, looking at how the algebra of symmetries is deformed, you get a deformed mass shell condition for point particles. In particular, for massless particles within this model that we are considering as example model, you get the maximum allowed momentum. And also you get that the way energy and the spatial momenta add up in interactions, so the laws of conservation of energy and momentum in interaction are deformed. Again, because of the deformation of your algebra of symmetries. And I will come back to this towards the end of the lecture today. Okay, so we start from here, and I want to go on and discuss, okay, so what can we say about the way particles propagate within such a model? For example, how does the word line of a photon look like? Once we have the phase space relations, which are these ones, and once we have the algebra of symmetries, so also the Casimir, then the evolution of the coordinates. This is just standard Hamiltonian construction. You do the Poisson brackets and you get the evolution of time and space coordinate. Putting them together, you can write the word line for a photon. And you see that this is exactly the same word line that you would write in special relativity. So the velocity of the photon, so you have x bar 1 and x bar 0 are the starting point of the word line, the ones that you want to consider a starting point. And then x1 and x0 are the space and time variable. Remember that we are in 1 + 1 dimension. So from here you see that we have a coordinate velocity, which is defined as the ratio of x.1 to x.0, which is 1. Well, c, it's c, but in these units it's 1. However, now the subtlety of the model comes, because you remember, we mentioned that the phase space is deformed and that the algebra of symmetries is deformed. This means, in particular for this model, that the action of translation on your spacetime coordinates is not the standard one. And in particular, well, for the space coordinates, if you translate by a translation parameter A, your space coordinates, you get the usual thing. So you translate by an amount A and you get x minus A. However, if you act with your translation operator on your time coordinate, you will get that the time coordinate is translated with well, x0 minus a0, which is the standard bit. A0 is the time translation parameter. And then you have an energy-dependent correction term. Here in these formulas, I'm only looking at the first order correction because it's enough to discuss what I want to discuss. We don't need to do the full non-linear corrections that we have, for example, here. This fact, so the fact that translations are non-trivial means that two different observers that are far away, far apart one from the other, if they use standard translation to describe what the other observer should see, they will get to wrong conclusions because they have to use the correct translation operators that work in the world they live in, which is this world with the deformed symmetries. To see what may happen, let us consider a scenario where we have Alice and Bob, as usually many relativistic thought experiments. Alice is emitting two photons. One photon has low energy and one photon has high energy. The low energy is blue, the high energy is red. From the point of view of Alice, the two photons have exactly the same word line because this is the word line that Alice will write. So according to Alice, these two photons will reach another observer, Bob, that is translated far away with respect to Alice at the same time. However, if you do things carefully, then you will know that, well, these are the two word lines for the two photons as written by Alice. You use your deformed translations to go to the reference frame of Bob, who is far away. And you do it with parameters A0, A1, and you ask that they are such that the low energy photon will arrive to the space-time origin of Bob. Okay, so they started from space-time origin of Alice, and you ask that the low energy photon arrives to the space-time origin of Bob. And here I am assuming that the low energy photon is low energy enough that we do not have to worry about any deformation effect. Okay, so this 1 over kappa, we mentioned we expect it to be roughly around the Planck scale. So this photon has energy much, much below the Planck scale. Okay, while the other one has a higher energy. And for the other one, we are considering the deformation. So we apply our translation operators to see the world from the point of view of Bob. And we discovered that for observer Bob, well, the first photon, the low energy one, will pass through the origin, because this is what we asked for. But then the high energy photon will not pass through the origin, but it will be a bit farther apart in space-time. In particular, it will get to the spatial origin of Bob with some time difference with respect to the low energy photon. And you can compute by how much, and you see that what is the time difference depends on the energy difference of the high energy and low energy photon. This formula here translates into, well, it's just being rewritten here in a way that is more useful for phenomenological studies. You write it as the difference in time of arrival, so this delta x0. It's 1 over k, you write it as eta over the Planck energy. So we said that we expect that kappa is order roughly the Planck energy. Here we use eta to say how much far away we are from the Planck energy. So this difference in time is given by the difference in energy over the Planck energy multiplied by the total distance that the two photons travel. So the total distance that separates observer Alice from observer Bob. And here I want to make few comments. So one comment is that this fact that the two observers, that to know what an observer is observing, you have to go to the origin, to the reference frame of that observer, okay? And this is one manifestation of this relativity of locality that I was talking about yesterday. So you have to specify in which reference frame you're looking at things. A second thing is that you can see that this formula for a time difference, so this time difference in general will be very suppressed by the ratio between the difference in energy and the Planck energy, because we don't see photons of Planckian energy, right? So we see photons of much lower energies. So this difference in energies, it will be many, many orders of magnitude below the Planck energy. On the other hand, another thing that we see is that this time difference grows with the distance travel, okay? And of course, because we are basically saying that the physical velocity of the two photons is different. And the more they travel, the more this will accumulate and become larger. And this already tells you that if we want to test such a formula, we really need to think about cases where we have as high energy photons as possible, and they travel for as a big distance as possible, or as a large time as possible, okay? And this is why we go to astrophysics, and I will discuss later. And the very last thing I wanted to comment on here is that this difference in the time of arrival, which depends on the energy, can also be understood as an effect of the curvature in momentum space. So yesterday we discussed that this kind of kinematical model can be understood as a model where particles have a curved momentum space. And in that, within that framework, this time difference is basically exactly the same effect as energy redshift that you have when you have curvature in space-time. But when you have curvature in space-time, in our standard theory, we have that you have a difference in energy corresponding to a difference in when you are detecting something. Here you have the converse effect, so a dual effect. So you have a difference in time of arrival due to the fact that the two particles have a different energy. And it is interesting because at least in 1+1 dimensions, you can really write the formulas you would write for the Sitter spacetime, kinematics of point particles in the Sitter spacetime. Write the formulas that you would write for kinematics of particle with the Sitter momentum space. And you see that these formulas look very much alike if you exchange the role of space and of space-time and of momentum space, okay? Which is useful. Well, it is mathematically interesting, but can also be very useful to help create some intuition for what is going on, because some things may look strange, but then you remember that the dual thing already happens in curved space-time and everything makes sense again. Okay, so I mentioned that if we wanted to test this possible effect of the deformation of kinematics, we would need to go to astrophysics, because that's where we have the highest energies and the longest times of travel. We wrote this formula, but this formula was derived in a deformation of flat space-time model, so deformation of special relativity. When we are considering, oops, sorry, something is, sorry. when we are considering particles that come from some astrophysical sources and travel across the universe, we have to remember that our universe is curved. So we have to account for curvature here. And the one way to do it, it's not unique, and I will come back to that later. However, the one that is mostly used in phenomenological studies basically generalizes this, just saying that, in fact, you have to use, instead of the energy, you have to use the energy rescaled by redshift, because we know that in an expanding universe, we have energy redshift. Once you do that, your formula for the difference in time of arrival takes this form, where you have a function of the redshift here. And this function depends, for example, on the cosmological model that you are assuming. Here, I'm just assuming standard FRW model. And before one gets excited about this, what you want to do is to make some back of the envelope computation and see, okay, I understood that this is going to be amplified by the distance, but how big an effect I can get. So if you put in numbers, for example, assume that you observe some photons with energy order 10 GeV, which is something we observe relatively frequently, coming from gamma ray bursts. So these are big explosions happening somewhere in the universe, and these photons get all the way to us. The typical distance of a gamma ray source, so of a gamma ray burst, corresponds to a source placed at redshift equal 1. You put in these numbers in this formula, and you get that this 10 GeV photon will arrive with a time difference with respect to a low energy photon emitted by that same source. So with a time difference that is order 10 to the minus 1 seconds, which I would say is really impressive, because if you make the ratio of 10 GeV with the Planck energy, you get many, many orders of magnitude difference, okay? So you would expect something extremely small. However, the fact is that the distance, which here is encoded in this function d of z, is extremely large, and it can compensate and make up for most of this difference in orders of magnitude. And 10 to the minus second is something it's a human time scale, okay? It's something we can hope to see. This in an ideal world. Then, as I will discuss, there are many reasons why this is extremely hard. So let's say that the main topic of this second part of the lecture is you have to get your hands really dirty when you're doing phenomenology. I mean, you have this very small little formula that you want to test, that you derived from somewhere, and you think you're almost done, and then it's where the real difficult part begins, okay? And then still you want to get an idea about the magnitude of your effect, and you say, okay, but say that instead of 10 GeV, I observe a photon or another massless particle that has energy of 100 TeV. What would be the time of arrival difference with respect to low energy particles emitted by the same source at redshift 1? Well, in that case, you get a time difference that is 1 day, so it's quite large. And in fact, as we will see later, this is a problem, because when you have something that a time difference that starts to become large, how do you claim that the low energy particle and the high energy particle were coming from the same source? What astrophysicists usually do, experimentalists, when they want to claim that something is coming from the same source, well, they look for, do the two particles come from the same direction in the sky? And do they come roughly at the same time, or at least within a time window that is compatible with what we know about how long the explosion or whatever that emitted them lasted? Okay. If you start having very large time differences, then it becomes difficult to claim that two particles were coming from the same source. Well, you always have to read the fine print. Here there is a fine print. I mentioned that this is one of the possible formulas. I will come back to this later, but keep in the back of your mind the fact that this specific formula for the redshift function, it's not the only possibility. In fact, what you put here also depends on the details of the model that you want to test, okay? But for the moment, we are going to use this one, well, because it is the one that has been used the most. It makes a reasonable assumption, namely that energy scales with redshift in the usual way. So for the moment, we will keep it, but I will discuss other options later. So basically, this observation here was made first some 30 years ago. In fact, it appeared in a paper published in 1998. And we can think about this as what really gave birth to the field of quantum gravity phenomenology. This is why I'm spending a little bit of time on this specific phenomenological effect today. So it was realized that there were these sources of gamma rays that are gamma ray bursts in the universe, and they were producing photons that had just enough energy, and they were just enough far away so that within this model, very, very, very simple of time of arrival difference, you would get a time of arrival just big enough to possibly see it. So there was big excitement because it was, people started to, well, they had an example of something coming from quantum gravity that you could see. And well, since then, almost 30 years passed, and people got interested in this. Also, people working in experiments that look at different kind of sources in the universe got interested in this. And so there were several works trying to put constraints, studying different kind of sources and trying to understand better what you could do. Before I go on, I remembered one more thing I wanted to say. When you're doing this kind of study, well, there are two options. Either within your experimental sensitivity, you do not see any time difference between high energy and low energy particles. And then you put a constraint on this parameter eta. And since eta over Planck energy, here I wrote m Planck, but in these units is the same. Since eta over m Planck basically is telling you how big is the effect, your goal is to be able to constrain eta to within order 1, because then you're really constraining something at the level of the Planck energy. So if eta, you constrain it and it is much, much smaller than 1, well, I mentioned yesterday that you could have few orders of magnitude wiggle room around the Planck energy, but say that you find that eta, in order to be consistent with your null observation, has to be, I don't know, 10 to the minus 15. Well, then you can say that you are constraining very strongly your effect. But I mean, given how difficult it is already incredible if you can constrain eta to be order 1, order 10, less than order 1, order 10, okay? It's already a big result. The other thing that may happen is that you do see some time of arrival difference. Well, first of all, you have to exclude any other possible explanation for that. And then in that case, you may propose a measurement for this parameter eta. Okay, so these are the two scenarios that can happen when you do these kind of studies. I mean, not just this for time of flight, any kind of phenomenological study, okay? I think I saw something appearing in the chat. So this would be a good moment. Is there degeneracy with other possible causes for such a time delay? Okay, this I'm going to discuss in detail later. So if you don't mind, let me continue the discussion. And then if there is something that you had in mind that I didn't cover, you ask me the question again, okay? Okay, very good. So as I said, there are many, many studies so far. In particular, the framework in which there had been more studies, and the reason is that we have more data, meaning that we have observed many gamma ray bursts, is using gamma ray burst to put to constrain such an effect. And there is a very good news, meaning that at the moment, different groups have been able to put constraints of this kind. So say that eta has to be less than about order 1, okay? Order of magnitude, give or take order of magnitude. Well, no, much less than 1, there aren't really strong claims, but say less than about order 1. Oops. And an example about, well, very simplified example about how you do this, but just to give you a flavor of what the data look like. So this is how a gamma ray burst, so a bunch of gamma photons arriving to the telescope look like. Here, each line, this, and this, refers to the count of photons, so to how many photons you have seen within a given energy band. So these are different energy bands. And this, from left to right, is time, okay? So what happened here, for example, is that, so this is lower energy, this is higher energy. What happened here is that you didn't have any count, basically, so there was nothing going on. Then suddenly you have a burst. That's why they're called gamma ray bursts. So suddenly you count many, many photons within this energy band, also within this energy band. And then slowly everything disappears. So there is some astrophysical mechanism, some kind of explosion that we haven't understood completely yet, that sends to us all these photons of very high energy. Here we are around the order 100 MeV energy, and here we are counting photons with more than GeV energy. Now, if we zoom in here, because this is the part that is more interesting, the higher energy, these are the individual photons that have been seen by the telescope. Okay, this counts here. Again, this is time. But here now we are plotting the energy. So there was one photon that had more than 30 GeV for energy, and then a bunch of other photons that had order 1 GeV for energy. You see that this photon arrives more or less at the same time as the other ones. You put this information in your formula, you put in information about distance. We are able to infer the distance of gamma ray bursts by looking at their properties in the optical side, so very low energy side. Not for all of them, but for some of them. And the ones for which we can do it are the ones that are of interest for us. You put in the energy difference, and this is where this estimate comes from, okay? So this is a very simplified description of how you put the constraint, but gives you at least an idea. Now, what is the problem here is that we have no way of knowing that this one photon here had been emitted at the same time as this little group here. In particular, we do know that the explosion mechanism of a GRB will produce sometimes photons of higher energy, sometimes lower energy. In fact, here you see that there is a bit of a tendency, like first you see the low energy photons and then you see the higher energy ones. But this is compatible with what we know within our astrophysical models. But then our astrophysical model is still uncertain, so we have no way of knowing that this specific one was emitted at the same time as these ones. And in this sense, this constraint, it's interesting because it tells us that we can reach the Planck scale, but you wouldn't bet anything you care very much about that there isn't anything, that eta is not in fact larger than 1, because you have no certainty about the astrophysical model. And what you can do is to collect many observations coming from many gamma ray burst explosions and see if they behave in a coherent way, okay? So if you observe many different gamma ray bursts, say that they are coming from different distances, so different L, if there was any effect like this, you would see that for gamma ray bursts that are farther away, you are able to measure larger time differences, and for the ones that are closer to us, maybe you don't see anything because then it gets hidden in the mess of all the photons that are arriving. Okay, so the only way to see anything, but also the only way to exclude anything, is to do a statistical analysis of many sources, observe different energy ranges, because also you know that you should expect within this model that there is a specific relation between difference in time and energy. So you want to check for all of this. The unfortunate thing is that so far there are very few studies trying to do this. The main reason is that we didn't see many gamma ray bursts where the photons have energies larger than tens of GeV, which is barely enough to hope to see something. Okay, we see every day, we see on average a few GRBs. Well, not every day, but every week we see a few GRBs every week. However, most of them have lower energies, so they are not good enough for what we want to do. And for many of them, we are not able to measure the redshift, so the distance. So that excludes another bunch of possible data that we could use. Okay, so far we have order 10, 15 GRBs that we have seen that are good enough for our kind of studies. And people have started to try doing something, but I would say it is still very preliminary. So we don't have a final answer about whether when looking at photons, we do see or not see such an effect. I mean, we know that it cannot be too large. So we know that eta cannot be too large, otherwise it would be something obvious to see. But staying in the vicinity of Planck scale, we cannot really draw a definite conclusion. And this is what may motivate you to look for other kind of signal. And in particular, since roughly 10 years, we have a new kind of signal that we can use, which is neutrinos. so the IceCube collaboration in the South Pole was built recently, and since basically 2013, they know that they are observing neutrinos coming from somewhere in the universe. For most of the ones that they see, they don't know where they came from, but they can tell that they are of astrophysical origin, okay? And the neutrinos have a few advantages. Well, one of them is that we observe neutrinos at much higher energies than photons. And this is because photons, if they have too much energy, they interact with the radiation that is in the universe, and they don't reach us. So the universe is opaque to very high energy photons. Neutrinos don't have this problem. Neutrinos are weakly interacting. So even if they are very high energy, they can get to us. They don't, because they don't interact much, they don't interact with background, with magnetic fields, with anything. So they travel straight to us from wherever they were emitted. And as I was saying, because they in general have much higher energies, they have possibly much larger time of arrival difference if the effect is there. And when this difference is very large, then it is hard to claim that it came from a mechanism at the source, because these mechanisms, we don't expect them to last for too long. So this is something new that people have started doing in the last, say, 10 years, okay, looking at the neutrinos. And the idea is that you keep working on the photons, but you also look at the neutrinos, because you really want to either say that you are not seeing anything in a robust way, or you look for the best possible option to try and see something, okay? So the more variety of data you look at, the better. So now so is there any questions so far, or can I move on? I don't see questions. Okay, so I move on. I want to discuss briefly how do you do these kind of studies. As I said earlier, I really want to show you how dirty you have to get your hands when doing phenomenology. So what do you want to do? You take data about all the neutrinos that have been seen so far. Each cross here is one high energy neutrino seen by IceCube during 8 years. Well, yeah, during 8 years of observations, basically. Now they have been taking data for, well, a bit more, order 15 years, but this gives you an idea. The circle tells you what is the possible area in the sky from which the neutrino was coming from. And you see that for some of them, you have a quite good estimate of the direction. For others, you have a very bad estimate of the direction. In principle, better direction would be better, because then it would be easier to say, okay, they were coming from this source that I saw exactly in that direction. However, the ones with the good directional estimate have a very bad estimate of their energy because of how the detector works. Basically, the detector works by looking at neutrinos that interact with ice in the South Pole. And that is a very dirty signal, you know. For the ones for which you don't have a very good estimate of the direction, typically you have a much better estimation of the energy. So you, as a phenomenologist, you have to decide, which ones do I use? Well, in principle, you can use both, but you have to start from somewhere. And when you start from somewhere, you want to get as a uniform data set as possible, because it's easier to treat. And in the end, it turns out that it's best to start from the ones that have a bigger uncertainty in the direction, but a good estimate of the energy. So you take this catalog, and then you compare with the map of all the GRBs that have been seen, the ones that are high energy, the ones that are low energy, everything. Because with respect to the energy of the neutrino, which is order at least, say, 60 TeV upwards, even a photon with 60 GeV energy is low energy. Okay, so you can already make a comparison between the time of flight of these two. So you compare these two maps and you look for neutrino signal that is compatible, whose direction is compatible with some GRB signal. Of course, that is not enough. Then you also have to have an estimate based on the estimate of the distance of the GRB of what would be the possible time of arrival difference, and see if you fall within a reasonable window, okay? And you collect all these candidate associations. You will never be sure that, say, this neutrino was coming from the same source as this gamma ray burst here. With one single association, you can never be sure. What you can do is to select many candidate associations. So, for example, this one would be a candidate association. Select many of them and see if statistically they are doing something interesting or not. Chances are that some of the associations that you select are fake. Okay, they're not real. But this is just adding to the noise of your signal. You don't care, as long as you're doing a statistical analysis. Okay, and you will see in a second how this is done. One last thing I wanted to say here is that doing this kind of work, is interesting for two reasons. One is that we want to constrain this anomalous time of flight effect that I was talking about. The other one is that it gives us a chance to solve a puzzle in astrophysics. Because before IceCube started taking data, astrophysicists were all saying that GRBs, according to how they work, how they understood they work, should also produce very high energy neutrinos. So people were expecting to see a bunch of neutrinos associated with GRBs, okay? And so far, there hasn't been seen no neutrinos have been seen in coincidence, in space and time coincidence with the GRB, okay? So this is puzzling, even if you don't care about quantum gravity, you just care about astrophysics, and people have been asking themselves, where are all the GRB neutrinos that we were expecting? They have started to revise their astrophysical models because they don't see them, okay? And from the point of view of someone coming from quantum gravity, one possibility is, you're not seeing them because you're looking for them in time coincidence, but if there is any anomaly in the propagation, they will not come in time coincidence, so you will not see them if you do that, okay? So this is an interesting study for quantum gravity and for astrophysics. I see that it's taking me a bit longer than expected to discuss this part, so probably I will postpone the discussion about symmetries until tomorrow, not tomorrow, until next time. And I will take the last 10 minutes to finish discussing this part, if that is okay.
Giulia, this is mind-blowing stuff, so take your time.
Good. Yeah, I think it's really instructive to discuss really the details of this, how this is done.
That statement that no GRB and the neutrino coincidence is never found, that gives me goosebumps. That's so great.
But in astrophysics, so astrophysics is not a lab. It's a bit like cosmology. It's not a lab. We look at things, we make our models based on what we see. Then we hope that nature decides to show us something else that either confirms our model or tells us that the model is wrong. But when you don't see something, for example, you don't know if you are not seeing something because it's not there or because you are unlucky. It's not a controlled lab. And this is why it's so important to make statistical studies, because based on what you know, you can estimate how unlikely it is that you are seeing or not seeing something. And when that becomes very unlikely, then you start questioning your assumptions, okay? But it's really, I mean, you really need to learn to live with uncertainty, but also to quantify your uncertainty. Okay. Okay, so I was discussing what is the general idea here. I mentioned that for a first trial, it's better to use this larger uncertainty in direction neutrinos. And then you compare, as I said, all the catalog of neutrinos that satisfy this criteria and all your catalog of gamma ray bursts for which you know the redshift. Because if you don't have the redshift, you are missing one ingredient in the formula that you want to test. So it's really, I mean, it's still doable. In fact, in a previous work, we didn't have this information, and you can still find a statistical way to do it, but you get much more noise, so you get much more uncertainty. Okay, since for some GRBs we do have the information about redshift, let's use these ones and we reduce a bit our noise. It's a balance about reducing noise at the same time reducing your data set. So you want to balance these two things. Nowadays, there are enough GRBs for which we know the redshift that even if you're reducing the available data set because you're using less GRBs, you're happy because you're reducing more significantly the noise. So you decide to do it this way. So what you can do is, as I mentioned, oops, where is it? This is the relevant parameter. And I mentioned that there was a couple of preliminary studies where redshift information was not used, but still one could do something. And from these preliminary studies, one could estimate that if the effect was there, then eta would be roughly within this range, between, say, 10 and 30. You don't take this number as like a 1 sigma thing. It's a very rough estimate. So something between 10 and 30 seemed to be reasonable in that case. And so for this new study, where we had information about the redshift, we could say, okay, if eta is within this range, we can really plot a band, this gray band, in a plot where we have time of arrival difference and energy. This is already rescaled with redshift, with the d of z function that we had before. So that if the effect is there, as you can see from the gray band, you would expect a linear relation between energy and this rescale time. And we looked for all the possible associations between GRBs and neutrinos that would fall within this gray band, okay? This was the criterion for saying this is a candidate pair of neutrino and gamma photon. And in the end, there were 4 such pairs among all these possible associations. Of course, they are within the gray band because that was the selection criteria. Okay, so don't get impressed that they are within the gray band. What you can do to see whether this is interesting or not, well, first of all, you see how well correlated they are. So how well aligned they are, and the correlation is high. It would not be too low anyways, because we were asking that they were in this band, okay? What is interesting is that you can compute what is the probability that if you get a random set of neutrino data, a random set of gamma ray burst data, and you're sure that there is no association, what is the probability that by chance you find 4 that lie within this band? So this is the question you can ask. You don't get impressed because you find 4 in the band. You ask, what was the chance that this happened randomly if there was no time of flight anomaly effect, okay? And when you do it for this case, you find that the chance is 0.7%. So it is a small chance, but it is not that small. So consider that usually to make a discovery, you have to claim a 3 sigma significance. 3 sigma significance is a smaller chance than this, okay? It is interesting. I mean, if it was 10% chance, you would be less impressed because you had 1 in 10 1 in 10 times you would find this by chance, okay? But 0.7 is interesting. And now here comes something that is interesting just because it is illustrative of how when your laboratory is the universe, how important is luck sometimes. And so notice that this result here was posted on arXiv on January 23, 2025, 1 year ago. Well, tomorrow is 1 year ago. Nice. I just realized. And on February 12, so this is less than 3 weeks later, there is a big announcement by a new collaboration that is looking for neutrinos that is still in construction, basically, but they had some of the detector working. And they announced that they have seen the highest energy neutrino ever observed. And these neutrinos here have energy of at most few PeV, so 10 to the 4 TeV, okay? The neutrino they had seen had energy of around 200 PeV. Okay, so it is much more energetic than anything that IceCube has seen. This neutrino was of the kind that is called the track within this collaboration, which means that is the one that has a good directional estimate, but not a so good energy estimate, okay? But of course, once you have you're studying this, you see the most extraordinary event ever seen. You want to see what happens if you look at it within the model you are testing. So the first thing you want to do is to see if there is any gamma ray burst coming from roughly the same direction as this neutrino that had been seen. The neutrino is the red area, and you see that there is one black dot in there. So it's here. These circles are the 1 sigma, 2 sigma, and 3 sigma uncertainty for the position of the neutrino. And you see that there is one GRB that comes, that is in 1 sigma agreement, basically, with directionally with the neutrino. Then I mentioned that for this kind of events, you don't have a very good estimate of the energy. And in fact, the collaboration KM3net basically gave this distribution for the energy. So you see it is peaked around 100 PeV. The maximal probability, well, the median energy, which is basically what would be more likely, is 220. But then it could be even 1,000, okay, with very low probability. And here we have to find a new method to estimate how compatible this was with the GRB that was in directional agreement. So we took the estimate of eta that we had from previous studies, and we say, assuming this is true, we knew the redshift of the GRB because that had been measured. It was a GRB at redshift 3, so very far for a GRB, very exceptional GRB. Looking at the arrival time difference, so that GRB had been seen 14 years before the neutrino had been seen. Putting all of this together, you can estimate what would need to be the energy of the neutrino for delta T to be 14 years, given that Z is 3.1 and data is in this region, right? Because the only missing variable that you have in your formula is the energy. And so you have a corresponding to this band, you have an energy band, and the energy band happens to be this one. So it is within the high part of the probability distribution function that had been given by KM3net. Again, this is not something you estimate by eye. I mean, by eye, it looks good. What you want to do is know what is the p-value. So what is the probability of being due by chance? Okay, again, of being due by chance if this effect here is not there. So if neutrino propagates just at the speed of light as usual, okay? And so the level of directional and energy compatibility that we find between this GRB and this neutrino tells us that there is a 1.5% probability that we would have found this by chance if there was no anomaly effect. So again, it's a low probability, but it's not that low. It's not small enough that you can claim you're seeing anything, okay? Now, the obvious thing to do is also to take the plot you had before and also put this new data point on your plot. Of course, it lies within the gray band. Well, not of course, it lies within the gray band because there is a good energy agreement, yes. You see that it lies here. Now, what you would need to do is to compute what is the probability that all of these 5 points are the way they are. Unfortunately, as I mentioned, this kind of signal is different than these ones because this is a neutrino with an energy uncertainty very large and a very good directional precision. And for this one, it's the opposite. So we still don't know what would be the combined chance. But roughly, you can say that it has to be smaller than either of the two. So smaller than the 1.5 and the 0.7 because we are combining things. Okay. But this has not been done yet. And I think this is a very good way, a very good place to stop.